Okay, Assalamualaikum and a very good day to all of you. So now we are actually in chapter 12, which is electromagnetic oscillations. So we are going to discuss LC oscillations and also RLC circuit. Okay, let's proceed with the first one, which is LC oscillation. Okay, when it comes to the LC oscillation, is basically involves something with the inductor and also capacitor. Okay, inductor and capacitor. Okay, so before this we discuss about LR circuit. Okay, where you can actually see that the increase of current there not going to be instantaneously. Okay, because of what we have a inductor over there, which is going to produce induced EMF because of changing of the current. Okay, so same goes at the LC oscillation. Okay, so what happened here is you are going to have one capacitor that are fully charged. Okay, so we are going to start with a capacitor that are fully charged. Okay, so so as you can see that when the capacitor is fully charged, is going to act like a power supply, which is the value of fully charged capacitor will be equivalent to the potential difference of the power supply. Okay, so now I'm going to explain to you step by step on how this LC oscillation work. Okay, so we start with the capacitor that are fully charged. Okay, so I have this capacitor that fully charged. So example, this is positive and this is negative. Okay, and then what happened is going to be connected in series with inductor. Okay, and then here we are going to have a switch. Okay, so what happened here is, before the switch is closed, now your capacitor is fully charged, which means that here the energy stored for the capacitor, recall everything back, UE equals to 1/2 Q square C. Okay, so now your energy stored inside the capacitor, your energy store is going to be reside in the electric field of the capacitor. Okay, so what happened is when you connect into when you turn on the switch, what happened is definitely there will be a current flow. Okay, because of what? Okay, once you close the switch, charge going to be the capacitor going start to discharge. So means that the electron here are start to move in this direction. Okay, because of what? Because it's basically attracted to the positive terminal of this plate. Okay, so as you can see that the electron flow and the current flow going to be the opposite directions. If example your electron flow right now is moving anti-clockwise, your current flow going to move in the clockwise motion. Okay, so what happened is when you have electron flow, you are going to have a current flow. So when you have a change of current, because basically basically what happened is before the switch is open, the current inside the circuit going to be 0. So it means that the energy stored inside the inductor here going to be 0. Okay, because there's no change of current, so what happens, there will be no induced EMF. Okay, but once the capacitor start to discharge, so electrons start to leave the plate. So the rate of electrons start to leave the plate will be equivalent to the current inside the circuit. Okay, because based on what? Based on I equals to charge over time. Okay, so here I'm going to repeat the rate of electron leaving the plate will be equivalent to the current inside the circuit. Okay, so as you can see that before this we have 0 ampere, but once we start to discharge, so means that there will be increase of current, maybe 1 ampere and then start to be 2 ampere and so on. So because of this change of current, definitely inside the inductor there will be induced EMF because of rate of change of current. Okay, it means that what is the functions of the inductor here? The function of inductor here is going to limit the current flow. Limit the current flow. So what happened is the current inside the circuit not going to be instantaneously matched. Is going to be slowly increased because there's a induced EMF that going to produce a magnetic field that oppose the original change in the current inside the circuit. Okay, so what happened here is the current inside the circuit slowly increase. So what happened is because of induced EMF produce a magnetic flux that oppose the change in the current. Okay, so what happened here is the energy stored inside the inductor, inside the capacitor will be reduced. Okay, so the energy inside the inductor will be reduced because charge start to discharge. Because capacitor start to discharge. But where is the energy go? Okay, so the energy are going to store inside the inductor as the are going to store inside the magnetic field of the inductor. So the energy for the capacitor going to be decreased. However, energy for the inductor going to be increased. Okay, so once capacitor is fully discharged, okay, once capacitor is fully discharged, okay, so basically capacitor is fully discharged, which mean that the capacitor is already in neutral mode. Okay, so what happened when the capacitor is fully discharged? Current at this particular time going to be I maximum. Okay, so I repeat. Okay, electron are going to leave the capacitor, which means that what happened at the capacitor is going to discharge. Okay, so there's a current flow. So the current going to increase from 0 ampere, 1 ampere, 2 ampere, and so on up until it's going to reach I maximum. Okay, but it's not going to increase instantaneously. Okay, but once what does it mean by current reach maximum? It means that the capacitor already at that particular time is fully discharged, which is neutral. What happened to inductor at that particular time? Is there any induced EMF? Yes, induced EMF going to be 0 because for the Imax it means that the current already be constant. Okay, so what happened if your current constant? There will be no induced EMF. Okay, so but okay, this thing happens in like instantaneously. Once the capacitor is fully discharged, what happened and at a particular time the current I maximum but still flow in the same direction, then instantaneously after that, not instantaneously increase, instantaneously after that, what happened is the capacitor going to charging. Okay, it's like you discharge and then the current going to be maximum. Once it's going to be maximum, it's going to be charging. Okay, so what happened to the directions of the current and what happened to the polarity of the capacitor? Okay, so the current here, okay, I'm going to draw it back for you. Okay, so okay, at the I maximum, the current flow going to be in this direction, which is clockwise motion. So means that we can actually see that the current flow is clockwise. So what about? So the current flow clockwise, so means that this is going to be positive, this one going to be negative terminal, correct? Okay, we assume, we assume that we have here positive, we have here negative. The capacity at the particular time is neutral, but once it's going to be maximum, we assume that for the conventional current to flow, this one going to be positive, this one going to be negative. So the electron are going to start to charge back the capacitor. So means that the electron here are going to move in this direction, because it means that because the charge there going because the electron going to charge back the capacitor. So what happened to the polarity of the capacitor is going to be opposite with the original one. Okay, before this, the upper plate is positive, the bottom plate is negative. But now, because electron flow from here, from the bottom plate to the upper plate, so it means that when the capacitor is fully charging, this one becomes negative terminal. This one becomes positive terminal, because electrons are going to leave the bottom plate. So leave the bottom plate with a positive, and then it's going to accumulate at the upper plate. It means that it's going to be more negative. So as you can see that here, so it means that at this particular line, you can see that the polarity of the capacitor already changed. Okay, already changed. So when already changed, so it means that at this particular time, when the capacitor is fully charging, where is the energy going to be stored? At the inductor or inside the capacitor? Definitely is going to be inside the capacitor. Okay, so I'm going to repeat back for you just to make sure that you recall everything back. Okay, first thing first, you have a capacitor at the upper plate. Okay, and then right now, first thing first, your capacitor going to be fully charged. Okay, your capacitor going to be fully charged. Okay, and then what happens when you connect it to the circuit? There will be an electron flow where electrons are going to leave the plate of the capacitor, which means that at that particular time is going to be discharging. Okay, because of the electron flow, definitely there will be a current flow. Okay, so up until one time when it's fully discharging, when the capacitor is fully discharging, the I going to be maximum, and at that particular time there will be no induced EMF at the inductor, because current already be constant. Okay, but once it reach I max, the electron over there are going to start charging the capacitor. Okay, are going to start charging. It means that the electron going to flow, leaving the bottom plate of the capacitor here, and then going to accumulate at the upper plate. So what happens? The bottom plate going to have more positive value, and the upper plate going to be negative value. So okay, so at that particular time, what is the functions of inductor? Okay, like discharging is not going to decrease instantaneously. It means that the electron not going to discharging instantaneously. Same goes if for the charging, it's not going to charging instantaneously, because inductor over there are going to make sure that they have an induced EMF that oppose the change in the current inside the circuit. Okay, so what happened is IMAX. Okay, so what happens when it's fully charging? Okay, once it means when it's fully charging, it means that currents over there going to be 0. Okay, why? Because like I mentioned before, if the potential difference of the battery equivalent to the potential difference of the capacitor is going to there will be no current, because the level of there's just no difference. Okay, before this there is neutral, so we can actually say that when it's neutral, okay, we put as a 0, and then we have a potential difference of battery here. So because of this difference, then it's going to be start to charging or start to discharging. But once the level is the same thing, there will be no current flow anymore, because there will be no electron flow. Okay, So that's the reason why once you fully charge, the current inside the circuit going to be 0. But once it's fully charged, what happens back? Yes, the capacitor are going to start discharging. Okay, capacitor start discharging, the current inside the circuit start to increase, the inductor are going to produce induced EMF, and then once the capacitor is fully discharged, is going to have an IMAX at that particular time, and then is going to fully charging back. Okay, so what happened is capacitor is going to charging, and then the inductor and the current inside the circuit start to have an IMAX or I0, and that's the reason why we call as the LC oscillation. It means that the energy for the capacitor for the energy is oscillate back and forth between capacitor and inductor. Okay, so before this, your energy here going to be stored inside the inductor. Okay, so this one, okay, there will be no current flow, so Imax going to be 0. Okay, okay, so example, okay, you didn't connect to the means that the switch didn't connect it. So once you open the switch, what happen is the capacitor start to discharge, so the flow of current is going to be in this directions. Okay, and this one, what is the directions of the induced EMF? Okay, because the current inside the circuit start to increase, so means that the induced EMF are going to produce B in this direction. Okay, because it's opposed. Okay, but once capacitor is neutral, or we can actually say fully discharged. Okay, so this is neutral or fully discharged. Okay, so what happened is current here are current going to be maximum current, and here there will be no induced EMF. Okay, but once it start fully discharged, and the current there are going to be Imax, is going to charge back the capacitor. Okay, going to start back charge the capacitor. Okay, sorry, I forgot to mention that the energy here stored inside the capacitor, stored inside the electric field of the capacitor. But once it start to discharge, the energy are going to be transferred to the inductor, which means that the energy going to be stored inside the magnetic field of the inductor. So it's going to be 1/2 Li square. Okay, but once it's fully charging, it means that all the energy stored already in inductor. Yes, very good. Okay, but the amount of energy, the total energy here going to be constantly here, because there's no loss of energy, there's no energy transfer as a heat, and that's the reason why the energy before and after should be the same. Okay, so once the current is maximum and the capacitor start to fully discharge, instantaneously is going to change where the capacitor are start to charging. Okay, so what happened is, okay, before this your current flow in this direction, so now we as if this is positive terminal and this is negative terminal. Okay, so means that the electron flow will be in this electron flow going to leave the bottom plate and then accumulate at the upper plate. Okay, so what happened here is, the upper plate going to have a positive the upper plate going to be negative and the bottom plate going to be positive. Okay, once it's fully charging. Okay, what happened to the current inside the circuit? Current inside the circuit start to decrease. Okay, from Imax is going to start to decrease. Okay, because once the capacitor reach its full potential difference, there will be no current flow. So up until one time when the capacitor fully charged, the I inside the circuit going to be 0. But as you can see that before this is Imax and then it start to decrease. What is the directions of the inductor over there? Is going to be is going to be so right now the directions of induced current, okay, because electron flow here, so the conventional current is basically flow here, the conventional current flow to the clockwise motion. So because it start to decrease, the rate of change of current decrease, so it's going to be in the same direction. So means that this is direction of your induced EMF, which is going to produce a magnetic field that opposes the change in the current. Okay, got it? Okay, so once the capacitor is fully charged, the current inside the circuit going to be 0. Okay, once inside the current start to become 0, there will be no induced EMF because it's constant value. Okay, so once it start to be 0 and fully charged, then the capacitor start to discharging back. Okay, but the directions of current already changed, because once it start fully charged, this one become negative plate, this one become positive plate. So it means that the directions of the current going to be in this direction. Okay, yeah, okay, you can see that before this is moving in clockwise, now it's moving in anti-clockwise. Okay, the reason why this thing happened is because of the change of polarity of the capacitor. Okay, so once capacitor start to fully discharge, what happened is the current inside the circuit will be increased. So means that your directions of induced EMF will be in this direction. Okay, yeah, so means that as you can see that when it comes to the energy, okay, if we look at the energy point of view, so this is at this particular time the energy stored inside the magnetic field of the inductor. But now once it goes to this part, which is at this particular time the capacitor is fully charged, all the energy are going to reside at the electric field of the capacitor. So means that it's going to store inside the electric field of the capacitor. Okay, but once it's fully charged and the capacitor fully charged and the I inside the current going to be 0, it start to fall and then it start to discharging. What happened is the energy inside the electric field going to be reduced, but the energy inside the magnetic field going to be increased. Li square 1/2 Li square. So as you can see that this kind of pattern is like oscillation, which is back and forth. It means that the energy are going to change from capacitor to electric field to the magnetic field, and then the magnetic field to the electric field back, and the electric field back into the magnetic field. So it means that it's going to change back and forth between capacitor and inductor. That's what we call as the RLC oscillation. Okay, so in front of you, we have a proper diagram, and you can see that we actually compare it with the simple harmonic motion that you already learned in physics 1. Okay, so when you reach Amax, which is the maximum amplitude, basically what happens is your capacitor is fully charging. So it means that the energy stored as inside the electric field. Okay, but once it start to discharge, energy are going to store inside the inductor, inside the magnetic field of inductor. Okay, which means that at this particular time we compare it with the simple harmonic motion for this diagram, because here they are going to store as a 1/2 ks square, and after that is going to store here as a 1/2 mv square. 1/2 mv square is kinetic energy, so it means that is because of movement. So once the capacitor start to discharge, there's an electron flow. So that's the reason electron flow. So electron flow, we can actually compare it as a movement of kinetic energy. Okay. Okay. So once it start to fully discharge, okay, so you can see say that the I max here is the same goes as the V max here. Okay. So capacitor fully discharged, current is maximum. So what happened is start to charging back. But once it start to charging back, once it start fully charging, what happened here is the polarity of the capacitor already changed, and the current inside the circuit is 0. So here we can actually say that is basically the same as a negative a maximum amplitude. Okay. Now your polarity already changed, so definitely your movement of your flow of current going to be changed. Once it start fully charging, then it start to discharge back. So that's the reason why you can actually see that once it start fully discharging, I max will be equivalent to V max here. So you can actually compare it with the simple harmonic motion. Okay, so you can see that we are going to get this graph this graph of capacitor, this graph of LC circuit, but I'm going to show you why there is a omega Q naught over there. So we are going to start derive the formula. Okay, so this one you can actually see the oscillations between the capacitor and the inductor. Energy stored are going to change from capacitor to the inductor. Okay, so here, okay, and then if example, if energy store going to be constant, so what happen is, example, if the energy changing at the middle is going to halfly change into inductor and halfly change into capacitor. So it's going to be U total here is 1 over 2 L I square plus 1 over 2 Q square over C. So this is energy electric field inside the capacitor, stored inside the electric field of the capacitor, and this one is energy stored inside the magnetic field of the inductor. Okay, so it's going to oscillate back and forth, and that's the reason why you are going to get this kind of graph. Okay, so you can see that here the blue one is the energy of the electric field, the green one is the energy of the magnetic field. So what happens is, when energy fully stored inside the electric field of the capacitor, there's going to be 0 value of the energy stored inside the magnetic field of the inductor. Okay, but once it goes halfway, it's going to store halfly at the electric field and half going to be stored inside the magnetic field. But next, once the capacitor is fully discharged, there will be no energy there. So means the energy stored are going to be fully charged, fully at the inductor. Fully at the inductor. So you can see that it's going to be oscillate back and forth. Okay, so I already explained it on the diagram, so hopefully you understand, and there's an explanation here. Okay, so I already put here for you to compare, which you can see that is basically the same thing. Simple harmonic motion is like LC oscillation. Okay, so here you need to understand that rate of charge leaving or enter the capacitor here, okay, at a particular time the capacitor is fully charging, okay, fully charging, leave or is equal to the current inside the circuit. Once the switch is closed, the capacitor is begin to discharge, the energy stored in the electric field definitely decreases, which means that the energy already now stored in the magnetic field of the inductor. Okay, so once capacitor is fully discharged, means there will be no energy anymore. At that particular time, the energy going to be stored inside the inductor, inside the magnetic field of the inductor. Okay, so when the capacitor potential becomes 0, the induced EMF also 0, and that's the reason why you can actually say that the once the potential difference of capacitor decrease, okay, once the potential difference of capacitor decrease, induced EMF also decrease. Okay, yeah, okay, but because once the capacitor potential becomes 0, that's the reason why at a particular time the induced EMF also 0, because there will be no change of current, because at a particular time the current going to be I maximum. Okay, yes, this one, the current reach its maximum value and all the energy stored in the magnetic field of the inductor. Okay, during discharge of the capacitor, okay, but once it's fully discharging, then the capacitor start to charging back. Okay, so now the current continue in the same direction first, okay, but decreasing in terms of the magnitude, which is the current inside the circuit is decreasing in terms of the magnitude, and that's the reason why you are going to get your induced your directions of magnetic field same directions as the current original. Okay, but once it's fully charged, okay, once it's fully charging again, the polarity of plate is now opposite the initial polarity. Okay, and this process followed by the another discharge. Okay, once it's fully charging, and after that it's going to fully discharge until the circuit return to its original state, which is at a particular time all the energy stored now at the okay, which means that at this particular time the energy stored inside the electric field of the capacitor. So it's going to be U E 1/2 Q square over C. But then once it's discharged back, it means that the energy stored now is going to be inside the inside the magnetic field of the inductor. So that's the reason the energy going to continue to oscillate back and forth between inductor and capacitor. Okay, so now I'm going to show you how to get the formula for the LC oscillations. Okay, so we have the capacitor, we have a switch, and then we have the inductor. Okay, we have the inductor, we have a capacitor. Okay, so once the switch is closed, so now we are going to use Kirchhoff law, where basically, example, if this is positive, negative, okay, inductor, you can actually add like a resistor, so it means that the directions of the inductor over there going to follow the directions, the rules of Kirchhoff law for the resistor. Okay, so this one going to be negative, positive, negative. Okay, so if we come up with the equation of the Kirchhoff law, so the potential difference here for the potential difference of the capacitor going to be positive because it's moving from lower to higher potentials. But for the inductor, you need to follow the rules of resistor. The current flow is the same direction with the current loop, so it's going to be negative. VL equals to what? 0. Okay, so VC is basically Q equals to CV, so it's going to be Q over C. So this is going to be the voltage, the voltage for the inductor going to be L di over dt equals to what? 0. Okay, so you rearrange once that you are going to get negative L di over dt plus Q over C equals to 0. Okay, so I think you already remember that current is basically rate of change of charge, charge over a time. Okay, sorry, charge over time. So here we are going to put this negative because of what? The current the decreasing of the potential difference at the capacitor will be equivalent to the decreasing of the induced current. So this is decrease. This is basically for the induced current. Okay, so the charge. So right now the capacitor is discharging, that's why you're going to get negative here. Okay, so you put it here, so you are going to get negative L d over dt dq over dt plus q over c equals to 0. Okay, okay, so you're going to get negative L, also this is negative over here, you're going to get positive d square q over dt square plus q over c equals to 0. Okay, you divide everything with the L, so you're going to get this equation, d square plus q over LC equals to 0. Okay, so I think you guys familiar with this kind of pattern, which is this is basically the formula for oscillation. Okay, so we are going to use here q equals to q naught cos omega t plus phi. Okay, q naught over there is original one, which original one. Okay, so now you can actually see that this one is you need to differentiate two times for you. You need to differentiate two times for this. Okay, so it means that, okay, first differentiation dq over dt, you are going to get negative omega q naught sine omega t plus phi. Okay, but second differentiation, you are going to get negative omega square q naught cos omega t plus phi. Okay, you insert here to here, here to here. Okay, so you are going to get the formula, the new equations will be negative omega square q naught cos omega t plus phi, okay, plus 1 over LC here going to be q naught cos omega t plus phi. Okay, you factorize, you are going to get, you factorize, so means that it's going to be q naught cos omega t plus phi negative omega square plus 1 over LC equivalent to what? 0. Okay, so when you have this kind of question, so you can actually put that q naught cos omega t plus phi equivalent to 0. So here negative omega square plus 1 over LC equivalent to 0. Okay, so omega will be what? 1 over square root LC. So the angular frequency going to be 1 over square root inductor and capacitance, inductance and capacitance. Okay, got it? Okay, that's how you get the formula. Okay, so so right now, so we already have a charge here as a function of time. So we need to find the equation for the current as a function of time, because as you can see that there's a changing in current and so they're changing in charge. Okay, so that's the reason why we need to find the formula for current as a function of time. So now, so as you can see that the equation here, you put it here. Okay, so you are going to get I equals to negative dq over dt. Okay, I already differentiate this, which means that I differentiate from here. Okay, put it here. You are going to get I equals to negative omega q naught sine omega t plus phi. Okay, phi is a phase difference. This is phase difference. Okay, so now omega q naught is basically I naught, which is omega q naught. No, sorry, this is not going to give it become positive because you have a negative here, negative and negative cancel out, then you get positive over there. So I naught, which is this is the maximum current formula. Okay, so you can actually put it as a I equals to I naught sine omega t plus phi. Okay, so this is how you get the formula for the charge as a function of time and current as a function of time. Okay, we are not done yet because we need to find the energy oscillate between electric field and magnetic field. Okay, so I'm going to proceed with the next part. Okay, so as you can see that the total energy is the combination of total energy is going to be the combination of energy of electric field and also energy of magnetic field. Okay, so for energy of the electric field, we know the formula is 1/2 q square over c. Okay, so means that q is q naught cos omega t plus phi. So it's going to be 1/2 q naught square c cos square omega t plus phi. Okay, and then you have energy for magnetic field. So this is 1/2 Li square. Okay, you get the equations for the current before. I equals to I naught sine omega t plus phi, which means the I naught is omega q naught sine omega t plus phi. So you insert into the equations, they are going to get 1/2 L omega square q naught square sine square omega t plus phi. Okay, what is the formula for omega, like the previous we derived before? So omega equals to 1/square root LC. So you insert into that equations, so you are going to get 1/2 L 1/square root LC square q naught square sine square omega t plus phi. Okay, so here square root. Okay, so L can be cancelled out. So you are going to get 1/2 q naught square sine square omega t plus phi. Okay, so now we are going to insert this formula and this formula into this total energy. Okay, so you are going to get U total, okay, equivalent to 1/2 q naught square over c cos square omega t plus phi plus 1/2 q naught square sine square omega t plus phi. Okay, factorize the equations. They are going to get 1/2 q naught square c equivalent, okay, and then this one going to be cos square omega t plus phi plus sine square omega t plus phi. Okay, so based on the maths formula, this one going to become 1. So the final formula for the total energy will be U equals to total 1/2 q naught square over c. So this is how you get the formula for the total energy. Okay. Okay, so here is the okay, so this is the I already derived it for you, so you can actually see that. Okay, so it's basically the same thing like I'm showed to you before. Okay, so this is the graph, okay, which you can actually see that we have two graphs, which is the charge here, and then we have the current as a function of time. Okay, so you can actually see that when the capacitor is fully charged, the current inside the circuit going to be 0. Okay, but when the capacitor is fully discharged, you can actually see that the inductor going to have a higher going to store the energy of the magnetic field. Okay, and then when this capacitor now is fully charging but with a different polarity, you can actually see that the current inside the circuit going to be 0. Okay, so this is basically the the change of energy between the energy of electric field and the energy of magnetic field. You can see that when the energy of electric field is maximum, the energy of the magnetic field going to be minimum, which is 0. So it's going to oscillate back and forth, okay, because there will be no loss of energy. Okay, so you can actually answer this question. Okay, the question this question, which is LC circuit, I already give you the answer. Okay, and maybe you can actually try for this question, which is this is the extra question of the RLC circuit also. Okay, if you have any question, feel free to ask during online teaching class. Okay, so for this one, this is the conceptual questions. Okay, and then the first question asks you about in figure 30.14, between stages A and B, this one and this one, does the capacitor do positive work or negative work on the chargers? Okay, so here you can actually see that definitely capacitor going to do positive work because of why? Once the capacitor for discharging, it means that the electron need to leave the plate. So for the electron to leave the plate, they need the energy to move from one plate to the other plate. So it means that the capacitor going to give some energy to the charge to move from one plate to another plate. That's the reason why work done going to be positive. And what kind of forces does the capacitor exert on the charges to do this kind of work? Definitely is going to be repulsions, electrostatic force. Okay, because electrostatic force, because the electrons are going to repel by the negative plate and going to be attracted by the positive plate. Okay, so C, during this process, does the inductor do positive or negative work on the chargers? Okay, at this process, at this time, when the capacitor is discharging, the inductor going to do negative work on the chargers because of what? At that particular time, the inductor basically gain energy, which is stored inside the magnetic field of the inductor. Okay, so at that particular time, the energy of the electric field, energy inside the electric field, will be transformed to the energy of the magnetic field. So it means that all the energy at that particular time is to gain, not to oppose, not to do a work done on the charges. Okay, and what kind of forces do exert on these charges? So definitely is going to be electrostatic force. It means that because we have a change of currents, so they produce an induced EMF. So this induced EMF going to oppose the movement of charge over there, which means that it's not going to be instantaneously discharged. Okay, so it means that the force is going to be electrostatic force, even though inductor store magnetic field. Okay, so now we are going to discuss about the LRC circuit. Okay, so I think you are familiar with this kind of graph. Okay, so the LRC circuit is basically the combination of resistor, inductor and capacitor. Okay, before this we only discussed about the LC circuit, which means that at that particular time the energy is stored between the inductor, in between the inductor and capacitor. Okay, but once you have the resistor, okay, so you know that when you have a resistor going to change the energy from electrical to thermal energy, or we can call it as a heat energy. Okay, so means that the total energy before charging and discharging not going to be the same, because some of the energy going to be lost as a thermal energy. So that's the reason why the graph not going to be that perfect, which means that the energy are going to change between electric field and magnetic field. But now is going to have a damping effect comes from resistor, because the resistor going to transform the energy into internal energy, which internal energy is basically a thermal energy. Okay, so if I come up with the equations for this one, okay, based on the Kirchhoff law, so we have like here, okay, so the example, this is positive negative, so here going to be positive negative, so you are going to get the formula will be Q over C. So this is basically the capacitor potential difference. Okay, and then you are going to minus with the IR, and then you are going to minus with the LdI over dt. So based on the Kirchhoff law, the potential difference is going to be 0. Okay, and then you come up with the equations here. You are going to get Q over C. Okay, I here going to be I equals to negative dq over dt. Why is negative? Is because of charge is leaving the capacitor plate. So that's the reason why you get negative over there. Okay, because the charge leaving or enter the capacitor plate will be equal to the current inside the circuit. So you're going to get here is positive dq r dq over dt, and this one become positive also. They are going to be d square q over dt square equals to what? 0. Okay, you rearrange this formula. Okay, you are going to get formula that looks like a simple harmonic motions. Okay, please recall back for the simple harmonic motion. Harmonic motion is m d square x over dt square plus b dx over dt plus kx equal to 0. This is formula for simple harmonic motion. Okay, so here in here your b here is basically a damping constant. So here the one that going to control the damping effect for the LRC going to be resistor. Okay, so you I'm going to show you maybe in the other video how to get the formula for this one. Okay, I got it's not that important at this particular level, but it's going to be important for the next one when you learn further electric. Okay, but I'm going to proceed with the formula first. Okay, for the derivations I'm going to show you in a different video. Okay, so here you are going to get the damping effect. The damping constant value will be R is depends on is going to depends on the value of 4L over C. Okay, so 4L over C. Okay, so this is the damping constant. Sorry, this is going to be R square over there, which will be equivalent to the 4L over C. Okay, so it depends on the inductance and capacitance. So this is the so this is basically we call as a damping constant. So the one that actually control is resistor. Okay. Okay. Suppose that when you actually connected the inductor, the resistor and the capacitor in series, so what happened is there will be a loss of energy in the resistor. The magnetic field still okay, the inductor still acquire a magnetic field energy, is going to acquire energy which is stored inside the magnetic field, but it's not going to be the same value and it's not going to be constant. Okay, before this the total energy will be constant and going to change from electric field to the magnetic field, but now there's some of the energy going to be transformed as a thermal energy, and that's the reason why the value of the energy after like one oscillations and then as a function of time is going to be decreased, because most of the energy going to be loose in the resistor, depends on the value of the resistance. Okay, for this one, okay, like I mentioned before, we have the damping constants going to be R equals to 4L over C. So we for the damping oscillation, we can actually categorize it into 3, which is overdamped, critically damped, and underdamped. Okay, so what happened here is when it comes to the underdamped here is this one. Okay, underdamped, it means that is going to have a few oscillations. Okay, going to have a few oscillation before come to rest. Okay, before comes to rest. So which means that the value of R here should be less than 4L over C. Okay, for overdamped, okay, overdamped is going to be this one, the C, which means that it's going to take long time for it to reach equilibrium. Okay, which you can see that from the pattern of it is going to take a lot of time for you, a long time for this thing to reach to its equilibrium positions. Okay, so for the overdamped is going to be the damping constants would be larger than 4L over C. Okay, and the last one is critical damp. Okay, critical damp is the value of B, which means that for the critical damp, it means that it's going to reach the equilibrium position in the shortest time. Which means that the value of damping impact will be equivalent to R squared for L over C. Okay. Okay, so I already explained to you here the difference between under damp, the critical damp, and also the over damp. Okay, and then we are going to get the new formula. Okay, before this, our formula for the omega going to be 1 over square root LC. But now we need to find a new omega, which we put as a omega naught. And then we need to insert into our formula is the damping factor. So means that the square root of everything should be 1 over LC minus the damping factor, which is R squared over 4L squared. Okay. And that's the reason why you are not going to use this thing anymore. Cos omega t over phi. This is basically perfect, which means there's no resistor, but it's going to change into Q naught E is E negative R over 2LT. This is basically it means that you need to incorporate the value of damping into the formula. Cos omega prime t plus phi. So this is going to be the new formula. Okay, so for this kind of questions, I'm mostly going to ask you you need to detect which one is over damp, critical damp, or under damp, and then you need to know how to use the formula. Okay, basically I'm not going to ask you about how to derive it, because if like I mentioned before, the derivations is mostly for the further electrics, which means that when you go to the high level, this is very important. But at this kind of level, the damping oscillation question is going to be only that you need to insert the formula. Okay, so I already prepared the questions for you. So for the A, show that this circuit will oscillate. Okay, so from these three damping category, which one they're going to be oscillate? Yes, definitely is going to be under damp. Okay, so it means that when it comes to under damp, you need to make sure that your damping factor R squared should be smaller than your 4L over C. So you just insert the number. If your resistor square is smaller than 4L over C, definitely it's going to be oscillate. Okay, so determine the frequency. So as you can see, that frequency is the relationship with the omega is omega equals to 2 pi f. So for you to get the frequency, going to be omega over 2 omega over 2 pi. Okay, so omega here is not the normal omega. It's going to be omega not, because you're going to the formula already changed, which means that this one is 1 over LC minus R squared for L squared, square root everything. Okay, so you put all the numbers over there, so supposedly you're going to get the answer, which is 363 hertz. Okay, what value of R will make the circuit non-oscillating? So between these three damp category, which one circuit non-oscillating? Definitely is going to be critical damp. Okay, critical damp, it means that is going to reach the equilibrium position in the shortest time. So it means that you need to get your R squared should be equivalent to the 4L over C. Then you are going to get the value of R that will make the circuit non-oscillating, which is critical damping. Okay, I think that's all for now. Okay, so we are going to continue to the next chapter, which is the next chapter is we are going to find the value of phase difference and how to calculate the phase difference value in the LRC circuit, which is it's not going to connect to direct current, it's going to connect to the AC current. Okay, so okay, if you have any questions, feel free to ask. Okay, so I'm going to see you at the next chapter. So assalamualaikum and goodbye.